Hello everyone. Today we will continue with torque. Yesterday we started with this lesson and I explained what is the meaning of torque. So we said the torque is the turning effect caused for sure by what? By a force. So in order to have a torque we should have force. Force is what causes torque. Okay, when you exert a force on an object around a pivot, a fixed point or axis of rotation, so this object can turn, such as wrench or such as door, okay, such as seesaw. So when this object turns, we call this torque. Okay, the torque is a quantity in physics that were represented by the Greek letter tau, and it's written like this, tau. Okay, and it's equal, we said, to the force times the lever arm. So the definition of the lever arm is very important. Lever arm, we said that it is the perpendicular distance from where you start, always from the pivot to the line of action of the force. Okay, so the force is drawn on your picture, so you just extend it, okay, like a dashed line here, and the perpendicular distance drawn from the pivot to the line of action of the force is the lever arm. Okay, so simply torque is equal to the force times the lever arm. So why the lever arm, this perpendicular distance, and not this d, all of it? Because, girls, we said that only the perpendicular component of force is what causes the object to turn. Okay, but the parallel component of the force doesn't cause any turning effect, therefore doesn't cause any torque. Okay, so this is the equation that we are going to memorize for this section: force times lever arm, and lever arm is equal always for the length of the object times sine theta. Okay, the unit, what is the unit? If we are multiplying force by distance, therefore the unit is Newton for force and meter for the distance. Okay, so this is the equation again, and here you have these two figures. They are very important. Here let's find the lever arm together. From where we start from the pivot. This is the pivot. Okay, and you mentioned, girls, you see the line of action of force. This is the line of action of force. This is the line along which the force is exerted. Okay, by using a calculator, you bring a perpendicular from this pivot to the force. Okay, so this is here the lever arm, and what is the angle therefore between L, length of the wrench, and the force? It's 90 degrees. Okay, so let's apply this on our equation. So F, you replace it, F by its value, it will be given. D, the length here, it will be given. And theta, what is theta here? Is 90. And if you make sine theta, sine 90 on calculator, what will it give? It will give 1. So when the force is perpendicular to the distance d, here we have the maximum torque because the angle is 90 degrees, and therefore sine 90 is what? Is 1. Okay, sine 90 is 1. Okay, now when the force is not perpendicular, see, this is the line of action of force. This is the line along which the force is applied. Okay, and this is here the length of the this is the wrench itself. This is the pivot. If I bring this from here to here, will I make any perpendicular distance? No. You know for sure by using a ruler how to find the perpendicular distance. You extend this line, you can extend it as much as you want, and you bring the ruler and you make a right angle with the ruler, with the corner of the ruler. Okay, so this distance, therefore, now this is our lever arm, not this one. So this is the lever arm. This is the distance that I'm going to use in the equation. Okay, so this is the lever arm, and what is its equation? It is d times sine theta. So usually they give us the distance d of the length of the wrench, okay, and the angle. So if they give you distance and the angle, okay, so you find it from here, and the angle will be what? It will be less than 90. See, this angle is less than 90. Okay, so sine of 90 less than of a number less than 90 will be a number less than 1, and here the torque will be less than the torque produced by the force here, such as the first example. Okay, so in order to produce a maximum torque, always we exert the force how? Perpendicular to the axis of rotation. This is the axis of rotation because this is the line that passes through the pivot point. Okay, and sometimes they don't give, girls, the distance d and theta. Sometimes they give the lever arm directly. So in this case you are going to go with this equation, so it's easier. Force times lever arm. If the force and the lever arm are given, you just find their product, and this is the torque. Okay, so here also another example. Here the force is perpendicular to the axis of rotation. Okay, so here we have the maximum torque. See, they gave you the force 120 Newton, and the length of the wrench is 20 centimeter, which is the same as lever arm, and for sure we have to convert it to meter before we plug it in our equation. So 20 centimeter divided by 100 gives 0.2 meters, and this is the answer for the torque. So force has maximum effectiveness in producing torque if it's exerted how? Perpendicular to the wrench. Okay, now the force, is it perpendicular to this, to the axis of rotation, girls, to the wrench? No, it's not. Is this angle 90 degree? It's not. Okay, so in order to find the lever arm, follow this, what I'm saying now. You bring a line perpendicular from the pivot to the line of action of the force. So line of action of the force, you extend it. Okay, and so this will be, this perpendicular distance is the lever arm. So as you can see here, this perpendicular distance, this one, is shorter than the wrench itself. It's 15, and by applying the same force as here, 120, we are going to get less torque. Okay, 18, but in the first case we got 24, so that's for sure normal, because the force here, it's not exerted perpendicularly to the wrench, it's exerted at an angle. So in this case only the perpendicular component is going to produce torque. Okay, so that's why the torque is less. Okay, the third case, what about the third case? If your force, the same force, 120 Newton, you are exerting force, you are making effort, but this effort is parallel to the axis of rotation, is parallel to the wrench. So no matter here how hard you push, you will not be able to unscrew the bolt. Okay, because there is no perpendicular component at all. Okay, so please, girls, these are the only cases we have. So repeat them more than one time in order to grasp the concept. Let's find together the moment toe. What is the symbol? Is toe. It's like the letter T, like this. Toe. Okay, so toe is equal to force times lever arm, or I can say D times sine theta. This is the general equation. D is given 40, okay, and what about distance? D, it's 0.2. What about theta? Look, what is the theta between the force and the distance? It's 90. The force is exerted perpendicularly to the wrench, so it's a 0, and it's at 90, and sine 90 is 1. Sine 90 is 1. So I can directly just write what? 40 times 0.1 and it will be equal to 8 Newton times meter. Questions. Let's see the first one. Where should the cat push on the cat flap door in order to open it most easily? Where do you think? Here, in the middle of the flap door, or here near the hinges, or here at the farthest point from the hinges? For sure, where? Here, because the longer the distance from the hinges, the more torque, the more turning effect the force exerted by the cat will cause. Okay, so torque is force times distance times sine theta. Okay, so in case this distance is longer, that the lever arm is longer, so the torque will be more. So the answer, the bottom as far from the hinges as possible, because it will be much easier. Here, mechanics often use cheater bars to loosen stub-borne bolts. Look, this cheater bar, I told you this is like something we put it on the wrench to make it longer. Okay, a cheater bar is usually a length of pipe that fits over the handle of a wrench, which makes the handle longer. How do a cheater bar help the mechanic? How does it help the mechanic? What, girls? When we make the handle of the wrench longer, see, and you hold it from here instead from here. So here you are increasing what? The lever arm. And by increasing the lever arm, what are you increasing? The torque. And therefore, the turning effect of the wrench will be easier, and we can unscrew our bolt easier. Okay, we will see this together, but before I will talk about something called clockwise and anti-clockwise torques. This, it gives us a direction for the torque. See, Mark and Tim lift their feet off the ground. What will happen to the seesaw? Let's see. What do you think? So here for sure we have the weight of Tim, Fg, which is downward, and here I have the weight of Mark, which is also Fg, which is downward. Which one is more? Which one is heavier, Mark or Tim? Mark. So for sure this force will be larger than the force exerted by Tim. And where is the pivot? The seesaw is turning around which fixed point is here, at the middle. So as you can see, the distance here from the pivot to Tim is the same as the distance from the pivot to Mark. So the distance here, it doesn't affect the torque, the turning effect. What's affecting here the turning effect is the force. Which one has larger force? Mark. Okay, so let's see how will the seesaw turn. Okay, in order to see how will the seesaw turn, first we will see the direction of the torque produced by each one alone, each person alone. Let's start by Tim. The force is down, imagine. So the force is down. So this force is going to cause the seesaw, this part of seesaw, to go how? Like this, right? To follow this path, like this. So this path, is it clockwise or counterclockwise or anti-clockwise? It's anti-clockwise, right? We know the clockwise is like this. Sorry. This is how the clock works. But anti-clockwise is the opposite. Okay, so this is anti-clockwise. Now let's see this one. Now only focus here on Mark. Forget Tim. The force of Mark is down and the pivot is here. So this part of seesaw is going to turn around the pivot. The pivot is here. So how is it going to turn this part? In this direction. In this direction. See the arrow. See the arrow. So is it clockwise or anti-clockwise? It is. See, imagine the clock when it works. Is it with the same direction or opposite? The same, right? So this is clockwise. So first, when you have more than one force, you study each one alone. Okay, so on the left hand side, Tim creates an anti-clockwise torque and Mark creates a clockwise torque. Which one is bigger? Which one is more? Which torque is more? The torque produced by Mark. So what do you think the overall effect will it be? Clockwise or anti-clockwise? So always when we sit two people on the seesaw, we see directly the result. Okay, the one which is heavier, the seesaw will go down in his position. So the clockwise torque is larger, the one of Mark, than the anti-clockwise, so the seesaw will turn in the clockwise direction. Okay, why I talked about this example? To tell you that torque is a vector quantity. It has a direction. So torque is a vector and it has a direction. And the torque is positive, tau is positive, C plus tau, when it's counterclockwise rotation, when it leads to counterclockwise rotation. Torque is negative when it causes a clockwise rotation. So this we have to memorize it. Okay, so here the example, it's near to the example of the seesaw. Pay attention with me. Here is the pivot, okay, and you are, forget this one, focus with me here, girls. This is the pivot and you are, let's say here, pushing here at this point. So how will this bar move around the fixed point, around the hinge here, around the pivot? It will move like this, right or no? So yalla girls, think this direction, is it with the clock? Is how the clock works, like the same thing, or the opposite way? It is the opposite. Okay, here it's like we are going from number 6 to 12, not from 12 to 6, right? So it is the opposite, so it's counterclockwise, therefore the toe here has a positive sign, and the number. Here, now let's focus at this case. This is the first and this is the second. Number 2. Here the pivot, so the first thing is you have to look at the pivot, okay? Because the object is going to move around our pivot. The force, now you are pushing here, okay? So you will cause this bar to go how? In this way. So you ask yourself, this way, is it clockwise or counterclockwise? It is clockwise, so it should be what? A negative 1. Also here it's wrong, it's negative, okay? It's by mistake, girls. It's negative. The torque here is negative. See, it's written negative torque. Negative torque. You can see it again. See how? Okay. So the last thing is this example about the sign of torque. Imagine you have this wrench and you are applying force upward. So tell me, how will this wrench rotate? What causing the wrench to rotate is the force applied by you. So it will rotate how? In the direction, in this direction, right? So tell me, what is this direction? Is it clockwise or anti-clockwise? I think it is anti-clockwise. So therefore, toe is positive or negative? Positive. Okay, let's see, this cat is exerting a force here on the door, and how will this door move, girls? with the force like this, right? It will rotate like this. Okay, look at this arrow. Does it show the clockwise direction or the anti-clockwise? It is. Complete the circle in your mind. Complete it. And imagine a clock in front of you. So what is it? It is clockwise. So therefore the toe here, the torque is negative. So the wrench produces positive torque and the cat produces a negative torque. Why? The sign here is very important, because for sure in problems we should guess it alone. We should know what is the sign alone. Okay, so it affects the answer. So the last thing, we are going to see these two visual concepts about torque and the sign of torque.
Torque is a quantity that measures the ability of a force to rotate an object around an axis. When you use a wrench to loosen a bolt, the magnitude of the torque on the bolt depends on the magnitude of the applied force and the length of the lever arm. The length of the lever arm is determined by the angle theta. The lever arm is the shortest distance from the axis of rotation to a line drawn along the direction of the force. For a given force, a longer lever arm produces a greater amount of torque.
Okay, so the longer the lever arm, the more torque. Sure. Now this about the sign of torque.
Torque, like displacement and force, is a vector quantity. It has both magnitude and direction. However, if we assign a positive or a negative sign to the quantity of a torque to indicate its direction, we can treat torque as a scalar. The convention we will use is that the sign of the torque is positive if the applied force tends to cause a counterclockwise rotation. If the applied force rotates the object in the clockwise direction, the torque is negative.
This is everything. Here, girls, we have some examples. So I hope you solve them for tomorrow. Okay. But before the examples, I will tell you about something called net torque, sorry. Okay, sometimes we don't have one force exerted on the object. Sometimes we have two forces or more. Let's say that I have this piece of anything, okay, plastic for example, and you have two holes here. Okay, so you are tying a string from this hole and another string from this hole. So you are pulling in this direction and your friend is pulling from this direction. Okay, and we have here, this is the axis of rotation. So this object is rotating around this axis of rotation. Okay, so when you have more than one force exerted on the same object, here you have to deal with each force separately. Okay, you find the torque exerted by force F1 alone, you find the torque caused by F2, force F2 alone, and you get the net torque by adding them. It's like finding net force. We find each force alone and we get net force, right? For the torque, it's the same thing. You find the torque caused by F1 alone and you find the torque caused by F2 alone and you add them together. Here an example. You have a seesaw here and you have two big masses, M1 and M2, placed on it. Okay, when I have mass placed on the seesaw, so I have what? Force, gravitational force, because it has a weight. Okay, the gravitational forces are always downward, and the distance here, it's from the mass to the pivot, or it's called fulcrum, from the pivot to the mass. So here, to don't complicate ourselves, I just focus at one object. I find its torque. How to find the torque of mass M1? By multiplying F times the distance, this one, right? I found it alone. Then I find the torque caused by M2. So it's the gravitational force of M2 times R2. I find each one separately and then I add them. Okay? For this one, I will do it with you. Calculate the torque exerted with a claw hammer. This claw hammer is used to pull the nail. Okay? If the person exerted a force of 80 Newton and distance equal to 25. So first, here as you can see from the figure, the force and distance are perpendicular. So we don't have any theta, we don't have anything complicated. We are just going to multiply the force with the distance and make sure to convert the distance to meter. That's all. So it will be 80 times 0.25, right? A wrench 30 centimeter long is used by a mechanic to turn a nut. If the force he exerts on the end is 5 Newton, the force is given and the distance is given. Calculate the torque. Very easy. For loosening a tight nut, which is better, a spanner with a long handle or a spanner with a short handle? What do you expect? Work on them again and answer each one on a piece of paper, please. Thank you.